Kia ora koutou, no mai, haere mai. Welcome to lesson 4 for introductory physics. This lesson is going to look at basic motion. We've talked about frames of reference. We've talked about the idea of vectors. Now we're going to use those concepts to describe how something moves. As usual, we'll just jump over and work through the slideshow. Lesson 4 on basic motion. Our goals are quite simple. We're going to define and hopefully understand distance, displacement, speed, velocity, and acceleration. And we're also going to hopefully explain the difference between average and instantaneous quantities quite simply. So the hopeful is about the simply. So we'll be able to explain them, but hopefully simply. Part 1 is distance and displacement. So what do we mean by these? First of all, what do we mean by motion? Motion, this whole lecture is about motion. We need to understand what that means. And that just means anything that's moving, essentially. Motion is just something that's moving. So a lot of physics involves studying motion, and we're going to look at some simple examples to start with and get slowly more complicated as we move through the course. Of course, we need to choose our frame of reference. We've already done that. There's a discussion on Stream about it. Please do participate if you haven't yet. The choosing of a frame of reference is a very important first step. So you do need to be able to do this without thinking too much about it. It shouldn't be a really long, difficult process. It should be something that you can do fairly simply for any given scenario. When you're doing that, you need to distinguish between 1D and 2D motion. Are we looking at motion in one dimension, in which case we can just use one coordinate, one variable, such as just x or just y, or are you looking at two-dimensional motion, in which case you need to keep track of two different coordinates, either an x and a y, or a distance and an angle. Once you've done that, you can choose your frame of reference, and then you can choose your suitable origin from which you will measure all the different points. So that is the prerequisite to doing any of the problems that we're going to look at. Any of the systems we're going to talk about, any basic motion needs this pure understanding of frames of reference, how to choose it, your dimensions, your origin, and all of that. So, definition of displacement. Displacement is just how far something has moved from where it started. The path it takes doesn't actually matter. So this diagram, you can see distance marked on, which we're going to talk about next, but displacement is just from A to B. Even though this object may have followed that blue dotted line, or indeed it may have followed any path, the displacement only cares about where it is versus where it started. Doesn't care about what it did in between. So that's displacement. You'll notice that it is a vector. It's got a direction, right? It's talking about where B is exactly in relation to A. So if you were using x and y coordinates, that would be some positive x and some negative y amount of displacement. You might instead use some angle relative to the fixed horizontal, in which case it would be negative some number of degrees, and the length of that displacement would be the magnitude. So you need both a direction and a magnitude for displacement. Distance is the length of the actual path taken. So however that object got from A to B, the length of that path is the distance. We already know that the shortest path between 2 points is a straight line. That's something that people tend to learn fairly early on in life, and it's sort of one of those sayings that gets thrown around. And the displacement is that straight line, that shortest path between 2 points. We don't care how we actually got there. That shortest possible line between 2 points, that's the displacement. But that means that the distance can never be smaller than the displacement. I should say than the magnitude of the displacement, because the quickest possible path is to go straight from A to B, and that is how we define displacement. So the shortest possible distance is equal to the magnitude of the displacement, but the distance can easily be much, much longer. In fact, you can have something with no displacement that has a big distance. It goes for a big circular walk and ends up back where it starts. As I already said, displacement is a vector. Distance, of course, is a scalar, because we don't actually care about the direction that the object was traveling in as it followed that path. All we care about is the length of the path. How much distance did the object cover as it followed the path? We don't care about the direction. Displacement, though, does care about the direction. It cares about exactly where it finishes compared to where it starts. In one dimension, this is all pretty straightforward. In one dimension, you'll remember that the direction of the vector can be simplified to just a plus or a minus. You don't need to write the plus when you've got a plus or minus vector system, but it is a good habit to get into if you're still not confident dealing with vectors versus scalars or dealing with frames of reference. It's a good habit, and I will occasionally do that. As you will see here in this diagram, this person starts by walking 5 meters to the left, so that's a displacement of -5 meters. Then from that position, they walk 10 meters to the right, a displacement of 10 meters plus 10. Their total displacement from where they started, so when they were at the origin, where they started, to where they ended is plus 5 meters. Their displacement is just plus 5. It's just where did they start versus where they ended. It doesn't matter that he went to -5 along the way. The final displacement doesn't care about that. The final displacement only cares about where he started and where he ended. It doesn't care about what he did in between. The distance, though, does care about what he did in between. So if he walked from 0 to -5, that's 5 meters. And then he walks from -5 up to +5, that's 10 meters. So overall, he has walked 15 meters. So that person has traveled 15 meters. The distance of that path was 15 meters. But going back a slide for a second, the displacement was only +5 meters. Right, so the displacement is not the same as the distance in this case. It's important to note, this should be something that you don't even really have to think about by the time you've done a few physics scenarios, a few problems, and worked through the next few lessons. Distance can never decrease. Distance is the length of the path you have traveled. Even if you turn around 180 degrees and walk back exactly the way you came, just like we saw with that man in the previous example, even if you do that, you are still traveling more distance. You can't undo traveling that distance. You can't go back in time and undo it. So distance can never decrease. Distance is only ever increasing. Displacement, of course, can decrease, because if you walk one way and then turn around and walk back, your displacement is literally decreasing as you walk back towards where you started. So displacement can decrease, but distance can never decrease. It can increase and it can stay stationary, but it can never decrease. In 2 dimensions, right, remember that we need a vector, we need a clear direction. The plus or minus are no longer enough information, so we can't just say he moves +4 meters. What does +4 meters mean when you have x and y directions to move in? Instead, we need to specify which direction he's moving in. So you'll see I've written he walks left 4 kilometers and then up 3 kilometers. So I've used left and up to define the directions. You could easily write that as I have on the diagram, as the first leg is -4x plus 0y, where I've clearly used kilometers as my unit. So -4 units in the x-axis. That's the first leg, which is left 4. And then the next one is 0x plus 3y, so up 3 kilometers in the y direction. The displacement at the end of this path is going to be the length of that final vector. So the vector that goes from where they started to where they ended. And of course, we can just use vector addition, because if we travel -4x plus 0y and then travel 0x plus 3y, those are already given in component form. We can just add them together, and therefore we get a resultant vector. So the total displacement is our resultant vector of -4x plus 3y. And now we can just use Pythagoras and SOHCAHTOA and get out our magnitude and our angle for our final displacement. So the magnitude of the displacement by Pythagoras' theorem is 5 kilometers, and the angle of that displacement is 37 degrees above the negative x-axis. It is more common with angles to give them in relation to the positive x-axis, in which case this would be 180 minus 37, or 143, if I've done that in my head correctly, 143 degrees above the positive x-axis. That would be the more common way to say it. But as long as you're very clear about it, there's no ambiguity if I say 37 degrees above the negative x-axis. That's still perfectly clear. The distance, of course, for this person traveling 4 kilometers to the left and then 3 kilometers upwards is 7 kilometers. So their displacement was only 5 kilometers at an angle of 37 above negative x-axis, but their distance was 7 kilometers. As I mentioned early on in this course, language can be important, and distance and displacement are a couple of words. Aside from being different in terms of one's a scalar and one's a vector, one cares about the path and one doesn't. Aside from all of that we've already talked about, It's also important to understand how we use the words, in the sense that displacement is a property of an object. You can say that an object has a displacement, but you can't say that about distance. You can't say an object has a distance, that makes no sense. But you can say that it has covered some distance, or it has traveled some distance. So there is a slight distinction about the way we use these. The displacement is a property of an object, but a distance is a property of a path, the path that the object has taken. So keeping in mind that distinction can also help you remember what they mean and figure out the values in any given problem. Units should be no surprise here. They're both lengths. They're both going to be in meters. Well, the SI unit rather is meters, but they can be any unit that has the dimension of length. So in metric, that might be meters, kilometers, centimeters, millimeters, nanometers, and so on. There is imperial as well, which we will never use in this course, but you should be aware of them. You can always Google if you encounter a problem and you need to convert, about yards, miles, inches, and so on. And there are actually other length units. Again, we won't use any of these. Light year is one that we do use in physics fairly regularly. I don't think we'll use it in this course. But there are all sorts of other abstract units like chain, rod, cubit, and the Hubble length. And those have specific definitions, but you would have to go and look them up if you ever encountered them. And I mentioned briefly the word dimension. I said any unit that has the dimension of length. And sometimes that's a useful concept to think about, the dimension of a property, of a quantity. So when we're talking about a quantity, we always give a number and a unit. So 5 meters, right? That's a number, a value, a quantity, and a unit. You have 5 of these meter units. Sometimes we want to talk about the concept of distance or displacement, but not actually a specific quality. So we want to do not a specific quantity. We want to do a qualitative discussion about distance or displacement. And in that case, it doesn't really make any sense to say meters or centimeters or kilometers, because we haven't actually given a value. And if there's no value given, the units don't really make a lot of sense. So in that case, what we can do is just stick with this concept of it being a length and not actually specify a unit. And in that case, what we're doing is called dimensional analysis. So when we're just thinking about concepts and things qualitatively and using just their dimensions, then we call it dimensional analysis. And length in this sense is a dimension, and we represent it just with a capital L. Sometimes you'll see dimensions written with square brackets around them. I tend to do it to make it really clear I'm talking about a dimension, but you'll also see them sometimes without it. So that is something that we will come back to occasionally, and it's just a useful check sometimes when you get a formula out and you want to check that dimensions all make sense. The other thing we'll do is introduce symbols. When we are talking about equations for values, so if we're talking about how somebody's position changes over time, we don't want to have to write full sentences out to describe this. We want to use mathematical equations. As I said, maths is a required tool for doing a lot of physics. So we want to have symbols that represent these different quantities. For distance, the most common are x and d. We also get y when we're talking about vertical distances, is very common, but realistically you can use any variable you want, any letter, any symbol, anything. You can literally use anything you want as long as you define it and make it clear that that is what you are using to represent this distance or displacement. For displacement, it is common, I shouldn't say it's common, it is one method of representing a vector to draw a little arrow above it, as I've done there with the x with an arrow above it and d with an arrow above it. That arrow is just saying this quantity represents a vector. But that said, there are a lot of times we don't do that. It's not consistent. So you won't always have an arrow above it when it's a vector. There's plenty of times, whereas I'll do this too. I'll just write x and it means a vector, but I haven't drawn the little vector symbol above it. Indeed, with as we'll see with speed and velocity, same thing. There's a lot of instances where we'll just write letters and they mean a vector, and we haven't given that little vector symbol above it. What that means is that there is no solution here. There's no tip or trick, nothing for you to memorize, no rules to learn. You just need to be able to think about the scenario, think about the system, think about the physics, and figure out what that quantity actually is. Are we talking about a scalar property, a vector property? Are we talking about distance, or are we talking about displacement? This is part of the doing physics. It's the bit that, as I said, a lot of teachers skip over. They'll just go straight to writing something on the board and they won't really talk about it. I'm trying to do that. I'm trying to do the talking about it. This is part of it. When you have a vector or scalar quantity, we don't always differentiate symbolically. So you need to be thinking about the system and figuring out what it is that you are looking at. So no matter how good your maths is, if you don't understand this distinction between scalar and vector, displacement and distance, if you don't understand that and you can't look at a scenario, look at the explanation of the system, and look at the equations and figure out whether this is for a scalar or a vector, then you are going to struggle, right? It's not something you can do just with the maths. It's something you need to have the physics knowledge of, the understanding of the system to be able to then use the maths to solve it. Moving on to the next step is speed and velocity. These are things that people are generally familiar with, even if you haven't done physics. We're used to talking about speed, especially with things like vehicles. So we normally have some idea of what we mean, but I'm just going to start right at the basics and assume you've never even heard of speed or velocity. We've already talked about motion. These sentences all mean the exact same thing. An object is changing position, an object's displacement is changing, an object is undergoing or experiencing motion, or an object is covering some distance. These are all ways of just saying that that thing is moving. But of course, we want some way to describe that motion. We want to define how it is moving. We've already defined displacement as its current position relative to its starting position. So if we describe how that displacement is changing over time, then that would tell anyone who's interested exactly how the object is moving over time. And that's exactly what we do. Let's go back to our one-dimensional person walking along. Suppose we watch them and they move 2 meters to the right every second. Their displacement is changing at a rate of 2 meters every second. I should say +2 just to be consistent. +2 meters every second, 2 meters to the right every second. This is the rate of change of their displacement. And that is exactly what we call velocity. So velocity is just the rate of change of the person's displacement. If their displacement changes by 2 meters every second, then their velocity is +2 meters per second. It's a vector. Since velocity has a magnitude and a direction, if I say +2 meters per second, that is the opposite to saying -2 meters per second, because -2 or -2 meters per second would be moving 2 meters to the left every second. Right, so there is definitely a direction involved. They are different if you say to the left or the right, but they both have a magnitude. So we've got a magnitude and a direction. It is a vector. Units, hopefully you can figure out the units based on how we've been talking about it. We said the rate of change of displacement, or how many meters this person has moved per second. Meters per second. We've already just said it right there. Right, so displacement per time, length over time, we have meters over seconds. It is common to write that as m/s or m(s to the -1). So when I say s to the -1, that means s to the power of -1. But that's the same. If you remember our exponent talk, that's the same as 1 over s, which is the same as saying m over s, which is what we wrote on the left. So m over s, or m(s to the -1, or indeed you might just say meters per second. Again, dimensional analysis, if we're not dealing with specific units, you can think about dimensions. Dimension for displacement was length, and for time is just time. So we have a length over a time, so L/T or LT to the -1. Any units that match those dimensions are acceptable. Moving into 2 dimensions, again, we no longer can just use plus or minus. We now have to specify the direction of the velocity very clearly. In this case, I've decided this person is walking up at a 45-degree angle to the horizontal. We don't need to do any trigonometry for that, because we can see that +2x + 2y is going to be exactly halfway between the x and y axis, which is 45 degrees. So they're moving +2x + 2y every second. And we can use Pythagoras to figure out the magnitude of that. So that is 2.83 meters per second at an angle of 45 degrees to the horizontal. So that's their velocity in 2 dimensions. And you can write that either way. Again, both are acceptable. You can put the x and the y, the components, so 2x + 2y is their velocity, or you can put it as a magnitude and a direction. Both are fine. But you do need to make sure you've always got magnitude and direction. So if I just said this person's moving with a velocity of 2.83 meters per second, that means nothing. That is not a velocity because I haven't told you the direction. So defining velocity more formally, mathematically, we have velocity is the change in displacement over the change in time, which, writing that out as a formula, again, I've used the little vector arrows there, but you do need to be ready and happy to use these sorts of equations even without the vector arrows. Velocity is equal to the amount of displacement that has been changed over the time that it took to change that displacement. That little triangle symbol simply means change in. So we would read that as velocity is equal to change in displacement over change in time. That is how we would say that. And I'm using the symbol V to represent velocity. As an example, a man is walking in a straight line with velocity V equals 4 meters per second. You'll notice I haven't put the plus or the minus there, but we've been told it's a straight line and we've been given a positive number even though I didn't write the plus sign in. So that means they're moving in the positive X direction or whatever direction coordinate you choose. I've used X. If he starts at displacement X equals 0 meters at time T equals 0 seconds, what is his displacement after 5 seconds and after 10 seconds? Now you could just jump straight to the maths, but instead we're going to just talk this equation through. This scenario through. If he is moving 4 meters every second, then after 1 second, he's moved 4 meters. After 2 seconds, he's moved another 4 for a total of 8 meters. I think I said 4 seconds. After 1 second, he's moved 4 meters. After 2 seconds, he's moved another 4 for a total of 8. After another second, he's moved another 4 for a total of 12, and so on. And you can see that by the time he's traveled for 5 seconds, moving 4 meters every second, he will have traveled 20 meters. Likewise, if he does that for 10 seconds, he will have traveled 40 meters. And so I didn't actually use the formula. I didn't look up a formula and write out what it meant. I just thought about what the scenario was and what these values actually mean and figured out the result that way. So that's more of a physics-based approach. And that's something you should be able to do. Just think about the quantities. Don't remember the formulas. Just think about the quantity. What does velocity mean? It's how much the displacement changes every second. And therefore you can figure out how far he's going to travel based on some amount of time. Of course, you can do that mathematically, and it's not bad to do it mathematically. I just want you to make sure you can do it without just looking up the formula. Don't just look up the formula and write out the results and do your calculation. Anyone can do that. A computer can do that. What we need humans to do is to think about the scenario and understand it, and that's doing the physics. So if we were going to do it mathematically, our formula is velocity is change in displacement over change in time. We can rearrange that by multiplying both sides by change in time, and we get the change in displacement is equal to velocity times the change in time. Change in displacement, therefore, for 5 seconds is 4 times 5, which is 20, and 4 times 10, which is 40. Those are the exact same calculations we did when we talked about it physically. We just didn't start with the formula. We actually started by thinking about what the values represented. How fast are we going? Sometimes we don't care about the direction. Sometimes we only care about how fast we're actually moving. So that is the magnitude of the velocity and not the direction. Sometimes we don't care about that direction. If I'm traveling down the road, I don't care about which direction I'm going in terms of my speed and my adherence to the speed limit. All that matters is the actual speed, the magnitude of that velocity. And indeed, that is called the speed. The speed is the magnitude of the velocity. Speedometers in vehicles are a good example of this because they don't care about direction. They just tell you your speed. Since velocity was the change in displacement over time, you might have already guessed that speed is going to be the change in distance over change in time, and indeed that's exactly what it is. So now nothing is a vector, everything is scalar. We've got speed, which is a scalar, just a magnitude, no distance, no direction, and distance, which is just a magnitude, no direction over time. So these are not vectors, they are just scalars. You may also see the symbol S used for speed. Personally, I'll stick to using V for both speed and velocity. As I said, sometimes I'll put the arrows above them, sometimes I won't. what you need to do is make sure you can follow along, think about the physics, and make sure you understand which quantity is being represented. The units and dimensions for speed are exactly the same as velocity, because our dimensional analysis never included a mention of a direction. It was just talking about the dimensions. We don't care if you're moving north, east, south, or west. We just care about the magnitude of that in terms of the dimensions. For the dimensions, the magnitude is what determines the dimensions, not the angle, not the direction. What happens if the person, or indeed any object, is not moving with a constant speed? So far we've been talking about ideas where everything's constant. We had someone moving at 2 meters every second continuously. Then we had someone moving at 4 meters every second continuously. What happens if that speed is not constant, but it's changing? So that person's speeding up and slowing down. What happens then? What we do is we differentiate between the instantaneous speed and the average speed. So instantaneous speed is what their speed is at any one instant. So it doesn't matter what they were doing and what they're going to do in the next instant. All that matters is what's happening at that very instant. What's the rate of change of displacement at that instant? And again, this is what speedometers show you. If you're in a car and it says 50 kilometers an hour, and then you brake slightly and your speed drops, then your speedometer will drop slightly and it'll tell you your new instantaneous speed. So the speedometers are only ever showing you instantaneous speed. Speed can never be negative. Just as distance can never decrease, then speed can never be negative. Remember that speed is the rate of change of distance. And if distance is never getting smaller, then speed can never be negative, because a negative speed would mean distance is decreasing and distance can't decrease. So negative speed doesn't make any sense. Average speed is the other half of that instantaneous speed. So average speed is the average over some time interval. So you might go for a 5 kilometer walk, and you might do it in 1 hour. So you've walked an average of 5 kilometers every hour. But while you're walking, you're not sticking to exactly 5 kilometers every hour. Right? Sorry, it was 1 hour, so that doesn't really make sense. But you're not sticking to that exact speed the whole time. You're not sticking at one speed for the whole hour. You'll be walking a bit faster in some bits and a bit slower in other bits and so on. So that instantaneous speed can be changing, but the average speed is determined by the whole time interval. When we've talked about the formula so far, we've used that triangle to mean change in. So that means we are talking about average speeds. When you're talking about a whole time interval, you go from some time to some other time. It doesn't matter how big that time interval is. The point is it's an interval at all. It's not just a single point in time. So if you've got a time interval, then you've got an average speed. Average speed in words. Average speed is the distance covered during the interval over the length of the time interval. So that's for when the average speed, when the speed is changing, you can use this to figure out the average speed. And that's the exact same equation as we saw for speed before. It's the exact same equation. It's just that your speed might be changing throughout that average speed one. If your speed was constant, then this equation here will tell you both the instantaneous and the average speed. But average speed, you just need to be aware that it can change within that time period. But the average is going to be given by that formula. So I've got an example here to hopefully drill home this concept. Stop-start man is sprinting 10 meters in 1 second, then waiting for 4 seconds, and then sprinting 10 meters in another second. So that motion overall has been 6 seconds. 1 second of running at 10 meters a second, then 4 seconds of waiting, and then another second of running. So that's 6 seconds in total. In total, he's traveled a distance of 20 meters. 10 meters and then 0 while he's waiting, and then another 10 meters, so 20 meters. While he is moving, so for those 2 1-second bursts, his instantaneous speed is 10 meters a second. And while he is stationary, his instantaneous speed is 0 because his distance isn't changing. Overall, though, he's traveled 20 meters in 6 seconds, so his average speed is 20 divided by 6, which is 3.33 meters per second. So his actual instantaneous speed was never 3.33 meters per second, but his average speed was. Instantaneous and average velocity is exactly the same. Right, exactly the same idea, the instantaneous change in displacement over time versus the average for some period of time. And we'll return back to stop-start man now. And this time, we've been given a little bit more information because we didn't have direction before because we didn't care. We were looking at speed and distance. Now we're looking at displacement and velocity. So we do care about the direction. So we've been given a bit more information. And this information is that, to start with, he sprints 10 meters to the right, plus 10 meters in 1 second, waits 4 seconds, and then sprints negative 10 meters, that's to the left, in 1 second. That means he's moved 10 meters to the right and then 10 meters to the left. It still took him 6 minutes. He still covered a total distance of 20 meters, but his displacement is 0 because he is right back where he started. That means his instantaneous velocity was 10 meters to the right, then 0, and then 10 meters to the left. But his average speed, his average velocity is 0 because overall his total change in displacement across that whole 6 seconds is 0. So his average speed might have been 3.33 meters per second, but his average velocity is 0 for that same time period. So average speed and velocity can be different. As I mentioned already, the formulas we wrote before were the change in displacement over change in time, which are for the average speed and velocity technically, since they both have time intervals in the denominator. If we want to talk about instantaneous velocity or speed, then technically the formulas become these next ones. Velocity is equal to the rate of change of x with respect to time, which is written as dx over dt. It's a calculus term, and if you've done maths or if you're doing maths, then this will make perfect sense to you. If you're not, then you won't have seen these before and won't be too sure what's going on. It doesn't actually matter. We're not going to deal with this. I just threw that in there in case anyone is familiar with that mathematics terminology. Feel free to use it, but it is certainly not required for this course. As we saw, average speed and velocity can be different in some scenarios. However, instantaneous speed is always equal to the magnitude of the instantaneous velocity. So the velocity might be positive or negative, it might have a direction, it might be in 2 dimensions, it might be any angle, but the speed is always the magnitude of that velocity vector, the instantaneous speed. If you think about distance and displacement, so there's the symbol use that I talked about, the little vectors above them, exactly the same thing here. The thing that I will keep repeating is that you need to think about the scenario, think about the physics. Right? I'm not going to sit here and tell you every single time, is this a vector or is this a scalar? I will to start with while we're in these first few lessons. But as we get further on, especially into section 3, where we start dealing with forces and so on, I'm not going to sit there and say vector or scalar every single time. You need to be comfortable and confident determining whether different quantities are scalars or vectors. There's also no generally accepted symbol to show the difference between average and instantaneous speeds or velocities. Again, you need to pay attention, you need to think about what's going on and think about what's being asked. If we ask you to determine the speed between time t equals 0 seconds and time t equals 5 seconds, then that's clearly going to be an average speed because we've given you a time interval to think about. But if I ask you what is their speed at 6 seconds, that's an instantaneous speed because I've just given you one specific time to figure out the speed for. So again, this is the physics of these kinematic scenarios, thinking about what the system is doing and what these quantities actually represent. And then, once you understand that, then you can bring that maths in and use the maths to solve the problems. And as you are probably already aware of the word constant, this slide should be pretty straightforward. Constant speed means speed is not changing. Constant velocity means velocity is not changing. And finally, the last kinematic quantity is acceleration. So we've met distance and displacement, we've met speed and velocity, and now we're going to look at acceleration. When distance is changing over time, we call it speed, or velocity if it's displacement changing. But what if speed or velocity is changing over time? We call that acceleration. Right, so acceleration is the rate of change of the speed of an object or of the velocity of an object. So if we've got an object that's initially stationary, so it's got no speed, it's got speed of 0 meters per second, but then it starts moving, After 1 second, its speed is up to 1 meter per second. After 2 seconds, it's up to 2 meters per second. After 3 seconds, it's up to 3 meters per second, and so on. That means that for every second, the object's speed is increasing by 1 meter per second. So that means that it's increasing at a rate of 1 meter per second, which we write as 1m over s squared, or 1ms to the negative 2, which we will define in a moment. Well, not define, you've just seen it, but we'll go back to that. Acceleration occurs whenever there is a change in velocity. This could be a change in speed, so the magnitude of the velocity vector might be changing, that's an acceleration. You might get a change in direction, so the magnitude might not actually change, so the speed might not be changing, but the direction might change. So if a car's driving at 50 kilometers an hour and they go around a corner, staying at 50 kilometers an hour the whole time, their speed has never changed, but their velocity has changed because it's changed direction. That means that they have technically accelerated. They have accelerated even though their speed didn't change. And of course, you can change both of those at once, which is also very common. So is acceleration a scalar or a vector? Technically, acceleration we treat as a vector. We don't differentiate the same way we have for distance and displacement or speed and velocity. Again, it's just another reminder that you need to constantly be thinking about the scenario. So if the speed is changing, then you know that an acceleration is occurring. But if the speed isn't changing, there might still be an acceleration if the velocity is. Right? So you need to remember that even a change in direction can be an acceleration. It doesn't have to be a change in speed. So again, as I said, I'm going to keep repeating this. You need to think about the system, think about the physics, don't jump straight into the maths. Make sure you cover all of this information first. Go through and say, is this a scalar? Is this a vector? What have we been given? What have we been provided? And what are we actually talking about? The most common example of acceleration is that due to gravity on Earth. That's because this is the one that affects our daily life just constantly. You drop something, it will accelerate downwards due to gravity. Gravity on Earth causes an acceleration of 9.8 meters per second in any object when it's free falling. That means if it starts from rest, if you let something go from rest, then every second its velocity increases by 9.8 meters per second. The green dots are just a representation of that. You'll see that the ball starts high, and then it drops a little bit, and then a bit more, and then a bit more. And so the velocity, the distance between, should say the speed, the distance between each of these points, the speed downwards is increasing every time unit, whatever that time unit that's been depicted as. The acceleration, hopefully no surprise here, it's the rate of change of velocity. So it's the change in velocity over the change in time, or again, the change in speed over the change in time. We won't technically use this one much because, as I said, change in speed is only one type of acceleration. You can also have a change in direction. So by doing the acceleration as a vector, this is why we generally treat acceleration as a vector. It will catch that acceleration as well, not just the change in speed acceleration. Units and dimensions. Acceleration, we've already seen, has units of meters per second. That means it's got dimensions of length and then time squared on the bottom. So length t to the negative 2. So any unit matching those dimensions is an acceleration. There are some interesting ones when you get into acceleration, aside from the simple yet uncommon ones like centimeters per second. That should have a negative in there. Apologies for that. Oh no, I put a slash. That's why I don't have a negative. Look at that. I'm reading it wrong myself. Centimeters per second squared. Inches, minutes to the negative 2. The next one, kilometers per hour per second. That is still an acceleration. It's saying how much your velocity changes in terms of kilometers per hour every second. And that is actually a common unit for acceleration when you're talking about performance cars. So high-end cars, they'll say they accelerate from 0 to 60 in however many seconds. That is an acceleration because you've given a change in velocity over a time unit. Even though the two time units are different, it's still an acceleration. Again, same concept with instantaneous versus average acceleration. Instantaneous acceleration is the exact rate of change of velocity at some specific instant. Right? So even if velocity, we've already discussed that if velocity is not constant during motion, that means that we've got an acceleration. This is true even if we don't have any average acceleration, just like we saw with the stop-start man, that was the name of it. The man walked plus 10 meters per second, then 0, and then minus 10 meters per second. So they had instantaneous velocity, but they ended up with an average velocity of 0. Same thing with acceleration. You might have a car that's traveling at 50 kilometers an hour at some point in time, and half an hour later it's 25 kilometers away and it's still going 50 kilometers an hour and it's still pointed in the same direction. So the velocity hasn't changed and they've covered the distance you would expect if that velocity had been constant the whole time, but they may well have accelerated and decelerated during that interval. The word decelerated, since I just used it, what does deceleration mean? An acceleration is just any change in velocity. Doesn't matter if your velocity is increasing or decreasing or just changing direction. Any change is an acceleration. A deceleration is an acceleration which causes the speed to decrease, so the magnitude of the velocity vector to decrease. That is called an acceleration. We still call it an acceleration. It's still an acceleration. Any change in velocity is an acceleration, but deceleration we sometimes use just to mean that the speed is decreasing. So is deceleration just negative then if it's always a decrease in speed? No, it's not. Because remember that you can choose your frame of reference. You might choose the opposite direction from the motion of the vehicle or whatever the object to be negative, right, or to be positive. So if you've got an object that's moving with a negative velocity, then that object decelerates. That means its velocity is getting less negative. That means that the acceleration must be positive because the rate of change in velocity, the change in velocity is a positive change. It's getting less negative. So a positive change, so you've got a positive acceleration, but it's still a deceleration because the speed is decreasing. So deceleration isn't always negative because you get to choose the frame of reference. In this course, we're going to stick to periods of constant acceleration. Right? Acceleration can and does change a lot of the time, but we're going to stick to constant acceleration. Sometimes we'll deal with problems that change acceleration, but for some period of time it'll have a constant acceleration, and then for another period of time it'll be a different but still constant acceleration. So we might deal with problems like that, but it'll always be constant within some time period. As an example of that, you've got a car that starts at rest. It accelerates at a constant rate for 1 minute, reaching a speed of 100 kilometers an hour. Then it stays at 100 kilometers an hour for 30 minutes, and then it accelerates back to rest in another minute. If we were analyzing that, then we would break it into 3 different time periods. The first minute, where it's accelerating with a constant acceleration, a positive one. Then a period of 30 minutes where it's got no acceleration. So the acceleration is 0 and the velocity is constant. And then the last period, which is the deceleration or the constant negative acceleration. It's negative in this case. Remember, it's not always negative for a deceleration, but it is in this case for 1 minute, which also which brings us back to a velocity of 0. So the velocity is going to start at 0, increase to 100 kilometers an hour, stay there, and then decrease again. And that's the 3 different time periods. Lastly, for this, I think this is the last one for this lesson, last part, the functions of time. So this is just talking about maths a little bit more and how we use that in terms of our physics. It's very common when we're dealing with physics scenarios for a quantity to vary over time. That's what we've just been talking about. A velocity is a displacement varying over time. An acceleration is a velocity varying over time. So it's very common to have quantities varying over time. And so we want to write equations to represent that because it's not always easy to write everything out in words and not always clear. An example where if a person is walking with a velocity of plus 2 meters per second and we call their start position the origin, then we know that after 1 second their displacement will be 2 meters, after 2 seconds their displacement will be 4 meters, and so on. So we know that that person is moving from 0 plus 2 meters every second. But if we can write that as a nice simple equation, then it'll be a lot clearer to communicate with other people that are concerned with the motion of this person. In the case of that person's motion, we could write x equals plus 2 times t, or just simply x equals 2t. In general, we could write it as x equals vt, where v is any constant velocity motion. And that is a function of time, right? X is, we can use this formula to calculate X based on the velocity and the time that we want to know the position for, or the displacement for. Sometimes if you want to be really clear that your function is a function of time, then you put a brackets with t in it after your variable that you can calculate. So this tells us that this equation gives us X as a function of time, and it is equal to velocity times time. So that is the end of this lesson. This was mostly just an introduction to these terms, to these concepts. It has been a fairly long one, 60 odd slides. Does seem like a lot, I realize, but hopefully you found that a lot of it was almost repetitive, right? We looked at displacement and distance, and then speed velocity. It mirrors a lot of the properties that distance and displacement had. An acceleration relationship to velocity is very similar to the relationship between velocity and distance or speed, distance or displacement. So hopefully there was not too many new concepts, not too difficult there. But once we've got these ideas, these concepts down solidly, then that opens up a whole world of physics problems that we can actually start to deal with. And that's what we're going to do in the next lecture.